Welcome to this video titled Congestion Avoidance with Preemptive Queue Drops. In this video, I'm going to define what is queuing-based congestion avoidance. We're going to look at some types of queuing-based congestion avoidance, and I'm going to specifically give you an overview of a couple of them called weighted random early discard and weighted tail drop. So what is queuing-based congestion avoidance? So there are let me back up here for a second. We know that QoS is all designed to deal with a situation where we have congestion. Congestion as defined by an interface queue is becoming saturated and is either reaching the point or has reached the point where it has no room left and packets now have to be dropped. And that can happen on the ingress side or on the egress side. Very rarely does it happen on the ingress as we're receiving packets. Most of the time we have egress congestion because we have a whole bunch of interfaces are feeding packets into a router switch and they're all being funneled to one outbound interface, and that's where congestion can happen. Now, we want to avoid that, right? We want to prevent that outbound queue from getting congested. At a high level, there's two ways to do that. We can implement QoS features that will act on our packets before they even get into that queue, so that queue will never get congested using things like traffic policers are typically done for that. Or we could implement some QoS features on the queue itself to prevent it from ever getting 100% full. And that's what this is referring to. So our goal here, if we want to do it this way, if we want to do queue-based congestion avoidance, we're going to end up basically randomly dropping frames as they're sent to that queue to keep that queue a little bit free, so it always has some room free. Okay, so on switches, there's a couple of typical ways you could do this. You could use weighted tail drop and weighted random early discard. A few switches also have their own method called dynamic buffer limiting. This is on a very small subset of Cisco switches. On routers, you can also do weighted random early discard. That's also available. So in this video, I'm not going to get into the gory details of how each one of these works. I'm primarily going to focus on the first two, weighted tail drop and weighted random early discard, just at a real high level to give you a feel for the differences between them. If you want some more details on these, operational details as well as how to configure them and how to modify them, I encourage you to go back to our INE website and look up some more advanced videos on QoS that we have that will go into the type of details that you're looking for. This is just to introduce you into these features. Okay, so both RED and WTD, or weighted tail drop, have some common terminology. Number one, they have something called drop thresholds. Now, both of these things, remember, both of these are features that at their heart deal with the queue and deal with this idea of, hey, as traffic is being directed to the queue, okay, so it's come in, let's just do it like this, just to give you a visual of this. So here is my egress interface. Here is the buffer or queue that's storing everything. And here are my ingress interfaces. Okay, and packets are being directed by the forwarding engine into this egress queue. Both weighted red and weighted tail drop at their heart have the same general purpose. The idea is, or I should say their same general way of doing things, which is, hey, rather than letting all this stuff into the egress queue, I'll just call it the transmit queue, let's drop some things even before they get there, like this guy. Let's just drop that, which will free up that one little space in the queue there. If I can delete it without deleting everything. There we go. And now that's freed up. So that's the idea behind both of these. Now they just do it slightly different ways. So the first thing is we have to understand this concept of drop thresholds. What is that? Well, drop thresholds, you have minimum and maximum drop thresholds. What do these refer to? These refer to when we're going to start dropping things. If the queue is completely empty, there's not necessarily a need to drop something. So you need to think to yourself, okay, as the queue starts filling up, and remember, if there's no congestion, the moment something's put in that queue, bam, it's gone. I mean, when there's no congestion, that queue doesn't get filled up at all. So the only time it starts filling up is that when we're putting stuff in there at such a fast rate that the egress interface just can't transmit it fast enough. So when that starts happening, now the first question you have to ask yourself is this. So imagine that this is my queue right here. Hopefully, it'll always stay right around here, really low. But as the packets start filling up, at some point, you're going to want to start dropping things. Dropping packets as they're directed to this queue. That's called your minimum threshold, when the drops begin. And then, if it keeps going up, you might reach another point where you say, hey, if it reaches this point, I really need to become about as aggressive as I can possibly get, so I at least have some room up at the top. That would be considered your maximum threshold. So let's take a look at how this could work as far as weighted tail drop is concerned. Now, weighted tail drop is not the ideal mechanism to do this, but on a lot of routers, and especially switches that do QoS and hardware, a lot of times you don't have a choice. You might have, if you turn on QoS, you might only have one thing you can do because it's done in an ASIC and you can't really change the behavior of that ASIC. So if weighted tail drop is your only option, here's how it works. So this is done on most switches, and it has some configurable thresholds and DSCP to threshold mappings. What does that mean? All right, well here, let's go ahead and dig into this. So, for example, with weighted tail drop, you could define one threshold, your minimum threshold, as maybe 40%, okay? Now, with weighted tail drop, here's the way it works. Not only do you define the threshold at a certain number, like, hey, when it gets to 40% full or 30% full, you also define, you say, okay, once I get to that level, at that point, as data comes in, I'm going to drop 100% of all the data that comes in if it matches a certain criteria, like this. We know that this is looking at costs right here, right? And let's just do a quick review of that. So we know that when you come to an IP packet, let's just deal with IP version 4 right now for simplicity's sake, that there's a toss byte in there, 8 bits long. And we know that IP precedence is dealing with the first 3 bits. And with those first 3 bits, let's just put this up here so I have a little bit more room, your precedence bits, you could have a value of 0 as your minimum value, up to a value of 7 as your maximum value. So what this graphic is showing is one queue that's, all of it is going in there. So we have an interface. Here's my interface, and here is his queue. And as packets are coming in from various other ingress interfaces, they're all going into this one queue. And by the way, on switches, a lot of switches, what they'll do, you might be saying, well, wait a second, Keith. This is saying cost, and you just talked about precedence. Yes. So a lot of switches, the way they will operate is that whatever the IP precedence is of a packet, sort of internally in the switch, you will never actually see this externally with like a packet sniffer or something, but internally, packets or frames will be given what's called an internal cost value, just for the purposes of queuing and QoS mechanisms. So a lot of times on switches, what they'll do is they will first discover what the IP precedence or DSCP value is, or they might set the IP precedence or DSCP value to some number, and then they will derive an internal cost value from that number, okay? But the main point I wanted to give was that just like IP precedence is a 3-bit value, costs is also a 3-bit value. So if I have an IP precedence of 4, that'll give me a cost value of 4. It's a 1-for-1 mapping, okay? So in this case, we have a queue here that's storing all of it. And the way weighted tail drop works is you say, okay, threshold number 1, I'm going to have threshold number 1 act upon these values, these cost values of 0, 1, 2, and 3. And I'm going to set threshold number 1 to a certain level, like 40%. What that means is that if we get to this level, if this gets all filled like this, we're at that level now, any packets that try to get into that queue with a cost value of 0, 1, 2, or 3, we're going to kill those packets. We're not going to let them in. Now you might say, but Keith, but look at this, we still have 60% of the queue that's unutilized, is empty. Doesn't matter. With weighted tail drop, you define a threshold, you define the values that map to that threshold, and once you meet that value, once you meet that number, no more packets can enter that queue that match those values. So in a sense, what we're doing here is we're saying, hey, all of this space is reserved for these cost values. Whether we're seeing them or not, whether they're coming into this queue or not is irrelevant. This value is reserved for them. And then typically the second threshold is set to 100%. Because clearly once we reach 100%, we've got nothing left. So you can see why I said at the beginning of this slide here that this is not an ideal situation, because if you set threshold value number 1 too low, like I did, let's say you set to 20% or something, well, that's a whole bunch of space up here, 80% of the queue, that might not ever be used. If for the next hour or day or week, the only packets that are allowed in here or they're being directed to here are 0s, 1s, 2s, or 3s, we're only giving them this much. 80% is just sitting there idle because we're never seeing the 4, 5, 6s, or 7s. But that's how weighted tail drop works. That's how it tries to reserve space in the queue for the more important traffic. Well, some very smart people, a lot smarter than me, looked at this and they said, you know what? This isn't very efficient. What would probably be better is if we said, okay, yep, I'll define a threshold. Threshold 1 at maybe, I don't know, let's say 40%. I'll do that. And I'll map some values to that threshold, but let's do something a little bit different. Why don't we do this? Once we reach that threshold, instead of just dropping every subsequent packet that comes in at this level, let's do it like this. Why don't we randomly drop some packets? In other words, let's say that all of these right here are packets that are trying to come in, and these have various values of 0, 3, 1, 2, 0, 1, okay? So they all map to this. Now, if I was doing weighted tail drop, we'd be done. We've already reached this right here. It's already this full. So all those packets would have to be destroyed. They would not be allowed in. But wouldn't it be better if we could say, you know what? Instead of doing that, why don't we do this? Why don't we start randomly dropping, like at the first threshold, when we hit that, why don't we start randomly dropping one out of 10 packets? So maybe we'll drop this guy right here. Let's just discard him and let the other ones in. Now, if the queue continues to get more full, then we can increase our rate of drop to maybe 1 out of every 5. And so now we'll be dropping a few more. That way, we don't have all this unused space here, but by doing these random drops, we're still leaving a little bit of room just in case the important traffic comes in. Wouldn't it be cool if we could do that? Yes, we can. And that leads us into the next slide, which is weighted random early discard. That's exactly what it does. So with weighted random, or I'll say red, with red, you still define your thresholds, but that's exactly how it works. When you hit threshold number 1, you start randomly dropping packets that were mapped to that threshold. So if threshold number 1 was set to 40% and it applied to packets with a precedence of 0 through 4, then that means if you reach that threshold, you're going to start randomly dropping some of those packets. Now it gets very, very complex as far as, well, what do you mean by random? Is it 1 out of every 10, 1 out of every 50? That is something that you can control, but we're not going to get into that. Just for the purposes of illustration, let's just pick a number and say 1 out of every 10 packets is dropped. And then you set a second threshold, threshold 2, maybe that's 80%, and that maps to IP precedence values of 5 through 7. And so the way this works is that once we hit threshold number, so from if we're at 0 to 39%, we don't drop anything. Everything is allowed into the queue at that point. Once I reach 40%, now at 40%, I start dropping 1 out of every 10 packets that have a precedence value of 0 through 4. Now, if the queue continues to grow and gets to 45%, 50%, then this rate of drop increases. Now it might start dropping 1 out of every 5, and then 1 out of every 3. Once I get to threshold number 2, this stuff gets dropped at 100%. So if my queue reaches 80% depth, at that point, no precedence values of 0 through 4 are allowed into the queue anymore. At that point, now I start dropping 1 out of every 10 packets that map to a threshold that map to 5 and 6s and 7s. And the rate of drop of these starts to increase if I climb above 80%. So that is how weighted random early discard works. And that concludes this video on queue-based congestion avoidance.